I don't know why. Hey, this no video is on only. Live?
Yeah, you are there.
Okay. Fine. Okay. Good afternoon. We will have a brief experimental demonstration of hysteresis band current control. Before going to that, a little bit of introduction I will give why there is a requirement of it. So when we talk about DC motor, so we have the field in the stator and the armature in the rotor, right? So out of these two circuits, one circuit is low power circuit and another circuit is a high power circuit. So whenever we talk about whether it is a transformer or rotating machines, in all we have two electrical field. So out of these two circuits, which is the low power, field circuit is the low power and armature circuit is the high power. The preferred location for the high power circuit is stator or rotor. So generally I give, most of the time first option will be the correct option, stator or rotor. So why it is the preferred location? Because the cooling will be better and the machine will live longer, right? In spite of that, knowing we are keeping intentionally the high power circuit in the rotor, right? So there I am asking a question, why is it placed in rotor? I am not giving any here, right? Why is it placed in rotor? Because we want something to happen for the conductors that is sitting in the rotor. We want the conductors, something to happen for the conductors. What is that? Current reversal. So when the conductors are under north pole, the current is perpendicular to the screen and inwards. When the same conductor comes under south pole, it has to be dot. If you want to have unidirectional rotation of the rotor, the current reversal should continuously happen as the conductors move from north pole to south pole and again south pole to north pole. So this current reversal is called commutation. So this for the commutation to happen, we place the conductors on the rotor because eventually we want the current in the conductors to be dash current, AC or DC? Anji? Yes, okay. Although it is referred as a DC motor, but the current in the conductors, in the armature conductors is AC. Now, so to improve the life of the machine, if we keep the high power circuit in the stator, then it will be cool and the life will improve. So for that, is there a possibility? That is the end of this slide. Is there a possibility to swap the location of high power and low power circuit? Right? So two options I can give here. Yes, no. Yes, right? If it is no, then we have to end the session. There is no point in continuing, right? So there is a possibility. Basically, commutator, what it does, it converts DC to AC in case of dash mode, motoring mode. Same commutator converts the internally induced alternating current to the DC in the external circuit. So the commutator plays the role of inverter in case of motor, and in case of generator it is a rectifier. Now we are not going to cover the generator, we will directly go to the motor. So commutator plays the role of inverter. So now what we do is we take the machine and the commutator, which is a mechanical system, we break it, throw it. Now we are bringing electronic inverter, electronic commutator. So that is what the next. You see, compare these two pictures. Both look similar, but what is the difference here? Yes, so they are changed. So this is stationary and this is going to rotate. In case of the so-called DC motor, right? So-called DC motor, the field is stationary, but here in this machine, the field will be moving. Okay. Now we want the current in the armature to continuously alternate based on whether the conductor see north pole or south pole. When the conductor see north pole, it has to be crossed. So this is for what what happened? Oh, I touched, right? What I have to do? Control L, no? No. Thanks. As the conductors see north pole, the current direction is one direction. So what is the current direction? Eventually the rotation of the rotor in the sense I'm talking about south north, right? Now we have to sense whether the conductors are seeing the north pole, then the cross. When the same conductor sees south pole, then it has to be changed to north. So this is done by the power electronic converter. So this power electronic converter can also be referred as commutator. Okay. So these are the three windings. So why we go for three phase? We can go for any number of phases also. The purpose of going for three phases, we want to make use of the commercially available the laminates and so on, right? Otherwise the cost will increase. Once again, if I go for 5 phases, then there has to be 5 legs. Once again, no, it has to be we have to make, and it is going to increase the cost of the system. So there we have all sensors, and we can also have optical encoder, so that we will see in one situation all sensors are okay, in another situation all sensors is not okay. So this is the field. The field could either be electromagnet or it could be magnet. So this will be rotating based on whether the conductor see north pole or south pole. That particular switches need to be considered and so on. So if I ask you, please identify the motor. So this motor is referred as electronically commutated motor. The motor which we have a DC motor, that we can say mechanically commutated motor, because it's not a DC motor, because externally you give DC, but actually for its working it has to be AC. So all are AC motors only. So that is a mechanically commutated motor, and this is an electronically commutated motor. At any stage, if there is something is not clear, you please interrupt. So this is the per phase circuit representation of the armature winding. I'm not showing the field here. The field is being accounted by having this induced EMF is K5 omega. When we apply a terminal voltage, there is a generating action is happening. We want electrical energy to get converted into mechanical energy. So while doing so, generating action is happening. So that is called induced EMF or back EMF. So there is a terminal voltage, there is a back EMF. So now the difference is going to inject or decide the current amount of current that is flowing in the winding. Now we have here battery, after that power electronic converter, which plays the role of the commutator. Current can either be this way or that way, right? It can be, or sometimes it could be zero also in a one particular phase. Current can be plus, current can be negative, current can be zero. All that we will see subsequently. Now this current is injected through the power electronic converter. The question is whether the current, this current, can it be decided randomly or based on something? Is it okay? Based on something. By mistake, I changed the option, but even then, yes, correctly at second one. Based on something. That something back EMF. So power conversion from electrical to mechanical form is effective if this product is constant with the time. This product in the sense E of t multiplied by I of t. So E of t multiplied by I of t is the power that is effectively converted from electrical to mechanical form. So this, what is the nature of E of t? Based on that, we have to inject the current. All right. So back EMF wave shape. So since we are saying that whatever current we are going to inject, it has to be decided based on what is the nature of the back EMF. Now we have to go to back EMF. How is the back EMF decided? Back EMF is based on the machine design, how the conductors are being distributed, what is the pole shape, all that. So back EMF wave shape depends on the machine design. Okay. Now there are two popular machines. Although we can make the machine to have any back EMF, what is commonly used is two machines. One is having a trapezoidal back EMF, another one is a sinusoidal back EMF. Right? We can go for any other wave shape also, but these are being widely used: trapezoid and back EMF, sinusoidal back EMF. So if it is a trapezoidal back EMF, then in place of field I have not shown. So there will be a field here which is sitting in the rotor, and if the field is not permanent, then that particular motor is referred as brushless DC motor. If the electromagnet is replaced by permanent magnet, then it's called permanent magnet motor. Now we are going to the next level of terminology. If it is a permanent magnet rotor, but the machine is designed such that the back EMF is trapezoidal back EMF, then that particular motor is called brushless DC motor. Suppose if it's a permanent magnet and if it is a sinusoidal back EMF, then that particular motor is called permanent magnet synchronous motor. If it's a trapezoidal back EMF motor, what kind of current we have to inject? Okay. So because we are looking for the product of back EMF and current, that should be constant with the time. right? If the power is constant with the time, what is that power? The power that is effectively converted from electrical to mechanical form. So that E of t, I of t minus some losses, friction, windage losses, subtract, if you subtract, then finally that is a shaft power, useful power. But since the efficiency of most of the systems are above 85%, we can say that E of t and I of t is very close to the shaft power, very close to the shaft power. All right. So now we are going for whenever the back EMF is constant, so that time we are giving a positive current. When the back EMF is constant but negative, that time you are giving a negative current. So if you go for this product, so then it is positive all the time. So this is just about one phase, right? So when you consider three phases, I'm considering a three phases. So if the current flows in one phase, then the current has to flow in another phase also, so that the path is completed. So that means at any time minimum of two windings need to be energized. It cannot, current cannot flow just like one phase, then it's open. So it will complete. So at any time two windings are energized. So in that case, that power waveform corresponding to another phase is going to be shifted in time. And if you add that, it's going to be constant with the time. Is this okay? Right? So why we are targeting for power to be constant? Because the shaft power we want to be constant with the time. So then if you go for a torque is equal to power by angular speed, that is also going to be constant with the time. The torque waveform you had seen in the lab yesterday, for induction motor it is more or less constant. And for switch reluctance motor there are a lot of ripple. So here also you will be having a constant waveform, although we did not show, but you can extrapolate that way. The torque waveform is going to be constant. So our objective is to obtain a torque waveform which is constant time, so that vibration, noise will not be. So vibration is not there, then the system is mechanically a sound system. Not about eliminating the irritating noise. Our target is not eliminate. Our target is to have a mechanical stable system. If the vibration continuously, then with the time there is going to be, right. So this is about trapezoidal back EMF. Suppose if the machine is designed for sinusoidal back EMF, so then what kind of waveform we need to inject? We have to inject sinusoidal current. I am talking about one phase, then we will go for similarly that we can use, right? So another waveform which is going to be in phase with the time. So this sin omega t multiplied by sin omega t, sin square omega t, which is 1 minus cos 2 omega t by 2. So this is 1 minus cos. So initially you can sketch minus cos 2 omega t, then the waveform need to be shifted in order to get 1 minus cos 2 omega t. So that waveform is going to be like this. This is about one phase. Now you have another two phases. Now how do I get this power, this constant waveform, but I am getting power waveform corresponding to one phase like this, but I wish to have this one. So what I have to go for? I have to energize all the two windings also, such that the currents are shifted by 120 degree in phase. So then finally if I add all those three waveforms which are shifted in phase, if I add, I am getting. This is the very basics of why do we go for system when we have a single phase system, because single phase power is pulsating with the time, changing with the time. We don't want the power to change with the time, we want the power to be constant. So the difference between the first motor, trapezoidal back EMF motor and sinusoidal back EMF motor, two windings were energized there, and the current is a quasi-square current. We should not call it as a square, because square means 180 degree positive. It's a 120 degree positive and 120 degree negative, and the remaining time is 0, right? So this is called quasi-square current, and that one is sinusoidal current. So the corresponding drives are referred as square wave drive. Although it's a quasi-square current, it's called square wave drive. This is called sine wave drive. Okay. So in the first case, two windings are energized at a time, and it is going to be a constant current for 120 degree. And for 120 degree, it is going to be a negative, and it's constant. In the second case, we are going to inject sinusoidal current. All right. So I may take some 10 more minutes just to tell the difference between the mechanically commutated motor means DC motor. Okay, I am avoiding the terminology DC motor because there is no DC motor. Anji. So there are two MMF vectors. One is a field MMF and another one is the armature MMF. Field MMF is pointing from north to south, and it is a stationary. Field is stationary. The armature is rotating. What is the direction of armature MMF vector? vertically downwards, right? So it's like this, right? Downwards. Now with the time this rotor is rotating, what will be the direction of armature MMF vector? Because we are going for a torque is FF cross FA. These two MMF vectors are to be done with the cross product. So I want to know, we want to construct the instantaneous torque waveform. What is the instantaneous, for which I should know every time what is the direction of FA? Always downwards, right? Always downwards, because after some time when it is rotated by 10 degree, let us say. So if you take a picture of the currents in the conductors, once again it is going to be the same. Agreed? So the conductors here are always going to be cross, the conductors here are always going to be dot. So with rotor movement, all the time if you see at a different time, so this is what is going to be the direction of current in the conductor. So all the time FA is going to be like this. So what is conclusion is, the MMF vectors are always making an angle of 90 degree between them. Okay, although the rotor is rotating, the MMF produced by the rotor, sketching this MMF vectors, one aspect considered, which is the shift of the magnetic axis, 10 degree, 5. It is a kind of an. The conclusion is the angle is very close to 90. That is produced, which is the cross product between FF and FA, it is always sin 90, it's always maximum. So whether such a thing is possible with electronic rotated motor, which is brushless DC motor and PMS, right? Brushless DC motor, what we are doing, we are energizing one winding with a constant current. When I say constant current is a dot, this is a cross. The resulting MMF vector, because of this excitation, will be pointing like this, right? So all the time, so quasi square current, I said, let's say 5 ampere. I don't know, Anshul will be doing with what ampere? 1 ampere, fine. Okay, so what he will be giving, 1 ampere constant, 0 minus 1 ampere. Okay, now let us talk about that 120 degree 1 ampere. 120 degree 1 ampere in the sense, so that 1 ampere will decide the length of this arrow, length of the vector, and it is always going to point in one direction. Okay. For BLDC motor, 2 windings will be energized, either AB, AC, BC, right? So the current flows from A1 to A2, then B2 to B1, start and finish and start and. So the current flows like this: A1, A2, B1, B2, B1. Sorry, A1, A2, B2, B1. If it is a A1, A2, the vector will be like this. If the current is from B2 to B1, the vector will be like this, because what I have shown is for the convention: A1, A2, B1, B2, C1, C2. If the current flows from B2 to B1, then the vector will be like this. So at any time you energize any 2 windings, the 2 vectors will be displaced by 60 degree. 2 vectors. I am talking about the armature excitation. Now we are not interested in the individual MMF vector produced by the winding excitation. We are interested in resultant. So the resultant will be making an angle of 30 degree. Okay. Now at any time it will be making. So now I go for, so total we have 360 degree. I'm considering a 2-pole machine. Therefore electrical degree is same as the mechanical degree. Okay, right? So we have 360 degree and we have 6 possible states. Current can flow from A1 to A2, B2 to B1. Then it can be B1 to B2, A2 to A1. Similarly for other 2 also, 2 more. So totally we have 6 states. 6 states in the sense the entire 360 degree is to be shared by these 6 states. That means that each vector will be at, let's say that it is here now 30 degree. After some time it will be maybe 90 degree. I'm going counterclockwise direction, 90 degree, then 150, then 210, 270, 330, once again 30, right? So anytime you energize, so we can displace the armature MMF space vector by 60 degree, either counterclockwise or clockwise direction, right? Okay. Now what we have to do, the rotor MMF is continuously traveling in the space, because the electromagnet is sitting in the rotor is going to continuously travel in the space. Now when the rotor is continuously traveling in the space, we have to decide where the MMF space should be, armature MMF, whether it should it be 30 degree, 90 degree, it is fixed. 30 degree, 90 degree, 150 degree, whatever we said earlier is fixed. That's clear, right? Because and we are also giving a constant 1 ampere current. So that is going to be fixed. Now the field MMF is here. So I am keeping the armature MMF here. And this armature MMF is going to be in space constantly at this point. Now when this is approaching, then I will shift this, right? When this is moving, this is not going to move because this is having a freedom to occupy in the space only at 6 distinct positions. 6 distinct positions. When it is approaching, you can't move. When it is approaching and I am observing it's coming very close, after some time, I am going to shift this. And it is going to be here for some time. But when I am saying that it is going to be here for some time, this will not keep quiet because it's sitting in the rotor and it is continuously moving. But this is there for some time. Is this understood? Right? So when field vector is continuously moving and armature MMF vector is stationary, so what will be the angle? The angle between these two MMF vector is going to change with the time, whether that is accepted. So if the angle between these two vectors is going to change with the time, that means the torque that is produced, that is also going to change with the time. Whatever I have explained, that is written here. Since we don't have time, we will skip. So torque is proportional to the cross product between field MMF and armature MMF. Field MMF is sitting in the rotor and it is continuously moving in space, whereas the armature MMF vector remains stationary in space for a time of t/6, where t is time required for one direction. Considering a electrical degree equal degree, otherwise what you have to see, this t stands for the electrical time period of the electrical cycle, you can say. Okay, so in case of DC motor, both FF and FA are stationary. Earlier I had shown the picture. FF is like this, FA is always like this, and the angle is 90 degree. So therefore you will get torque maximum all the time, right? Whereas here the angle between FF and FA is continuously changing. Why it is continuously changing? Because FA is fixed, whereas FF is moving, right? Now we have to decide what should be the optimum value. So the initial angle is theta, this is theta. Then when it is advancing by 60 degree, then this is going to be advanced by 60 degree. Okay. So the initial angle between FA and FF is theta I. The final is theta I minus 60. Is this statement understood? Understood. So what should be the value of theta I? That theta I is 120. So you can try, like initially it is 120 degree, right? So now when it is moving 110 degree, 100, like that. When it comes to 60, now what I do, I identify two phases. If those two phases are energized, then the angle once again becomes 120, right? So every time you energize two windings such that the angle between the FF and FA, angle between FA and FF is 120 to 60. Then again, two more phases are energized so that the angle becomes 120 to 60. So one electrical cycle will have such 6 variations: 120 to 60, 120 to 60, and so on. It's okay. So you can try initial angle is 100 degree, like 100 degree. So when it comes to 40, then 60, right? So then once again you can make 100 degree. So you find out, sketch the waveform, find out the average value. That average value is going to be less than what I said earlier, right? The initial angle is theta I. So the assignment here is determine the value of theta I so that the average torque that you will get for one electrical cycle is going to be maximum. So I have given the answer directly. You can write you can write. At the time of starting motor, I don't know what is the position sensor will be there. Right? Position sensors are there which will tell, and you will decide which phases need to be energized, right? So this 120 to 60 is the optimum value by which you will get maximum torque. That I will show you if it is there. This is what so when the angle is 120 degree, sine 120 is how much? Is equal to sine 60, correct? So it is a 0.866, right? Root 3/2. Then when it comes to 110 degree, Sine 110 degree. Sine 110 degree is sine 70, right? So it is gradually rising. So at this point, it is a 90 degree. So then 80, 70, 60. Once again, it becomes 0.8. Is this understood? Right? So the same pattern is going to be repeated. Now you find out the average value of this waveform. So you are getting some number. You try with this some other combination, that theta I 100 degree or theta, let's say theta I is 90 degree. So I want to have maximum value, maximum torque. So sine theta. So initially it is 90, right? So then after some time it becomes 80, 70, 60. So finally it comes to 30. So then I will display. So when the field MMF advances by 60 degree, then I will advance the armature MMF by 60 degree. So if you find out for that, it will be somewhere here, right? So we are interested in extracting as much as possible from the system. So finally, this is the optimum value. What is optimum value? The theta I is equal to 120 degree. All right. So whatever I had explained earlier, I will repeat now. FA is here and FC is here. The MMF vector due to energizing two phases at a time, Fn, and this is the resultant. Okay. So this is the, now you forget about the individual MMF vector. This is the resultant. And FF is this one. FF is south to north. It's pointing like this, and FA is like this. So the initial angle is 120 degree. Right. So now the south north pole, it rotates in the clockwise direction. But FA will be in the same location for some time. What is that some time? T by 6. T by 6. But once this comes to this position, the angle between the FF and FA becomes 60 degree. In that case, I will advance FA by another 60 degree. So then once again, the pattern repeats from 120 to 60. So like that, we have 6 states I have shown. So you can draw multiple diagrams in between also. Anji. No, it will be instantaneous. Instantaneous. FA is here, it will go like this. Why I'm saying instantaneous? Because this MMF vector is because of the electrical excitation. Now this rotor is moving. This FF is moving. So we have to talk about the mechanical time constant. Compared to this mechanical time constant, this is nothing. So we are advancing this instantaneously, but actually it's not instantaneous. You will have time constant there also, but electrical time constant is very, very less compared to the mechanical time constant. So here it's a comparison. So I will say this is instantaneously shifted by us with the help of the semiconductor device. All right. This is okay. FA is placed 120 degree. Okay. Field MMF is moving continuously in space, but FA is placed 120 degree. Then when the angle between FF, moving FF and the stationary FA is 60, then again I'm advancing FA by 60. Now once again the angle is 120 degree. FF is moving continuously, FA is stationary, that again shifting like that. So it's actually advancing the armature MMF vector in space in a discrete way. Discrete. Okay. So we require the position information not continuously, like no, approximately we want to know the position. So all sensor is adequate for sensing the rotor position, because we are not interested whether the field MMF has moved by 1 degree, 0.5 degree, that there is no requirement. Once it is 120 to 60, if it is very close to 60, then we are advancing. So all sensor is adequate. All sensor is cheap, relatively very cheap. Let's say 150 rupees. So with the 3 all sensors, because we have a 6 discrete states, 2 power n, where n stands for the number of all sensors, 2 power n should be greater than or equal to 6, right? If I take 2 sensors, so we are getting only 4, but we have to determine 6 distinct positions. So therefore we are going for 3 sensors, right? Now we are going for sinusoidal back EMF motor. Here all the 3 windings are energized. All the 3 windings are displaced in space by 20 degrees. All the 3 windings, the magnetic axis of all the 3 coils are displaced in space by 120 electrical degree. Now you are energizing those 3 coils by 3 signals which are shifted by 120 degree in phase. So whenever there is a match between the way the system is designed, how the windings are placed, and the signals which you are giving if there is a 120 electrical degree in space and 120 degrees in phase, if these two match, then we are having a magnetic field which is space, which you can call it as a rotating magnetic field, revolving magnetic field. Right now, the field MMF is continuously moving. Now, we wish to have 90 degree. If it is a 90 degree, then sine 90, which is maximum, then the instantaneous waveform is going to be constant with. If this is continuously moving, then we are looking for, can we get a magnetic field which is also continuously moving? So if this is 90 degree, when this is advancing by 5 degree, this is also advancing by 5 degree. If this is advancing by 1 degree, this. So all the time, if you can maintain 90 degree, right, then the torque is going to be constant with the time. So you can see that FA is placed 90 ahead of FF, and it has to move continuously in line with the field MMF movement. So for this, all the 3 windings are energized. So the requirement for creation of traveling magnetic, for you have the rotating magnetic field or rotating, but instead of calling a rotating magnetic field, I prefer traveling magnetic field. The technology traveling magnetic field. The reason is the same thing is being used in linear machine, magnetically levitated train. So if you use the word traveling magnetic field, that is more general than calling it as a revolving or rotating magnetic field. If I have to displace the armature MMF by 1 degree, I should know whether the field MMF moved by 1 degree. So we require an accurate position sensing, how much it has moved. Accordingly, we can energize the vectors with different. So we are energizing all these 3 windings by sinusoidally varying current, right? So what should be the magnitude of current? All that we have to determine so that this can be displaced. So accurate position sensing is needed, for which optical encoder we can for it. So this machine cannot be recommended for 2-wheeler, which I told earlier, but I am repeating it because optical encoder is expensive. So it goes to the consumer only. So that is why most of the machines, it's a brushless DC motor. If at all, if they are going for switching from BLDC to PMSM operation in the sense all the 3 windings are energized, that time they go for sensorless control. So initially, at the time of starting or during low speed, sensorless control is not effective. So we make use of the Hall sensor and we determine the position. Once it is catching some speed, then we can move from BLDC operation to PMSM operation. And the back EMF is also very close to sinusoidal back EMF waveform. So in Stark waveform, it's like a blank, I have not given. So it's understood it is going to be constant because all the time it is 90 degree between FF and FA. So it's constant. So the torque control, this is what we will show you, Anshul will show you experimentally. I may take few more minutes, 2-3 minutes. So if I have a winding, so this is the representation of winding. I'm not including this dynamically induced EMF, back EMF. I'm not. First, I'm explaining the concept. So if I have a winding and if there is a switch, semiconductor device, and if the switch is closed and if it is kept in the closed position forever, then the current will be rising like this. And finally, the current will become V by R. Okay. Now, we are interested in torque, certain amount of torque, which is most of the time we call it as a speed control, but better terminology would be torque control. That is a better terminology. Torque is equal to K phi I. K is a machine design constant, it is a flux, and this is the current. Now, if I want to have a lesser torque, so then I have to control the current. So if I leave it, close it, and finally the current in the circuit is decided by the resistance of the circuit. We don't want the current to be decided by the resistance. Actually, whenever we go for power, we are taking the control bias. We will decide what should be the current, right? So I want to have somewhere here. So let's say final current is 100 ampere and I wish to have some 25 ampere. So what I have to do? If I close it, eventually it's going to be 100 ampere after 5 times the time constant, right? So I want to have a 25 ampere. So what I do, if the current is, let's say 26 ampere, so then I will open the switch. So then 26 ampere is there, that is decreasing like this. Once the current becomes 24 ampere, then I will close the switch. Then again, current will increase 24 to 26. Once the current touches 26, I will open it. So the current is controlled between 24 and 26 ampere by closing the switch, opening the switch. So this diode is called freewheeling diode because it is playing the same role as that of the free wheel that we have in the cycle. We have a free wheel which is fitted in the rear wheel. So if you that free wheel, what it does, it will connect the rear wheel to the pedal movement. I do the pedaling. So then chain is there and there is a free wheel which is connected to the back wheel. When I do the forward pedaling, the free wheel is coupled to the rear wheel. When I do reverse pedaling, or I don't do any pedaling, that mechanism is not connected to the wheel. So that same free wheel mechanism we have. So this diode, what it does is it is connecting the source to the load only for the forward power. When the power is trying to go backward, right? So then it doesn't allow. So therefore this is called freewheeling diode. And this is called hysteresis band current control. Why it is hysteresis? Hysteresis means it is a hysteresis dependent. Hysteresis means hysteresis dependent. Whether you call it a hysteresis loss in the transformer core, rotating machines core, it is a hysteresis dependent behavior. Okay. So here also the change of switch from one state to another state, on state to off state. On state to off state, it happens at 24 ampere. Off state to on state, it happens at 26 ampere. When the current touches 26, I am turning off the switch. So when the current touches 26 ampere, right? So arrow mark is wrong. When the current is 24 ampere, then yes, so it changes from off to on, right? When the current touches 26, it is changed from on to off. So this is correct. Okay. So since the transition of the switch state from on to off or off to on is decided at two different current values, and when it will happen, it is depending on whether it was earlier current was rising or current was decreased. So since it is connected with the hysteresis, right? So that is called hysteresis band current control. All right. Now we wish to have quasi square current. This is what, for a BLDC operation, we want to give quasi square current. So quasi square current. Okay. This is the circuit you have, correct? Now, if I energize the transistor 1 and transistor 2, the current flows like this. So it is for 0 to 26 ampere. Now the current has touched, we will have a current sensor, all that. When the current touches 26 ampere, I open the transistor 1. Now what will happen? Since there is a current and we have an inductance, so T2 is kept on. So the current will flow through diode 4 T2. Is this understood? Now the current falls to 24 ampere. Once it becomes 24 ampere, this transistor will be turned on. So for this 120 degree, the transistor 1 and 2 are turned on. Then for some time, transistor 1 is turned off. Then again, transistor 1 is turned on. So for the complete degree, T2 is kept in the on state. The T1 is turned on, turned off based on the amount of current flowing in the winding. Okay. Now, after that, it is 0. None of the devices do conduct. Now we have to go for the negative current because this is what we are going to inject in the trapezoidal back EMF motor. So for this, the current, I should have given some name like this, A, B. So current should flow from B to A, for which transistor T3 and transistor 4 are turned on. So the current will go like this. So again, the current rises from minus 24 to minus 26. So then the transistor 3 is turned off. Then diode D2, B, A, transistor T4. Okay. So for this time, it is T3, T4 or diode D2 and T4. Is that okay? So next one is with the same battery, with the same power electronic converter, but for the winding, we want to inject sinusoidal current because the back EMF induced in the winding is a sinusoidal EMF. We want to match current and the back EMF. For that case, the difference between previous one, we have assumed 25 ampere as the reference current, either plus 25 or minus 25 ampere. But here, the reference keeps on changing. So initially, I say the reference is between 4 and 2 ampere. So once the current comes like, then I change the reference between 4 ampere and 6 ampere. Then I change 6 ampere to 8 ampere. Let's say the maximum is 10, 8 and 10. Once it reaches this, then I change the reference between 8 and 6, 6 and 4. So basically the reference keeps on changing, right? So with the same battery, it is possible to do that. So now let's consider the positive. For the positive, you have either the transistor T1, T2 are on, or the transistor T1 is turned off. So for this, earlier 24 ampere is the lower limit of the band, 26 is the upper limit of the band, whereas here the band is sinusoidal currents. Two sinusoidal currents you have to have the reference, the lower sinusoidal waveform and the upper sinusoidal waveform, and we have to see that the current is continuously falling in this two sinusoidal waveforms. Flux weakening I'm not explaining. If you want me to explain, I'll explain that also. I'll take 2 minutes for that. Okay. Okay. So this is the back EMF, and back EMF induced in one winding, and we are giving this current I1. So both are in phase. When the voltage and current are in phase, that means active power, right? If the voltage and current are displaced by 90 degree and current is lagging the voltage by 90 degree, then it's a pure inductor. If the current is leading the voltage by 90 degree, pure capacitance, right? If the current is like minus 30 degree, it's a combination of resistance and inductance, all right? Okay. Now, when I say active power, the electrical power is completely converted into mechanical form. Okay. Now this is how it happens. Okay. Now what I want, this is the flux, and flux coming out of the magnet. Since we have permanent magnet, we can't weaken the flux, we can't reduce that flux. So what we do is then we have to depend, because it's another circuit we have, the stator conductors we have, and we are exciting the stator current such that it will produce a flux, and that flux is going to oppose the flux coming out of the magnet. Okay. If the current is in phase with the EMF, whenever you have such a quadrature relationship, there is no coupling, there is no influencing. So now we are looking for whether this current can be shifted like this. There are two ways. One is the current can be shifted, current can lead or current can lag. If the current is lagging, then decompose into two components. One component will be in phase, which is active power. Another component will be in phase with the flux. So we are aiding. We don't want to aid. So we want to keep the current ahead of the back EMF. So then again decompose into two components, I1 and I2, where I1 is the torque producing current component or active power component, where I2 is opposing the flux, right? So basically, you have the induced EMF like this. With the help of our electronic converter, you synthesize a current waveform and ensure that the current waveform is leading that of the back EMF. In that case, flux weakening is happening, because the current and this current produces a flux which opposes the flux that is coming out of the magnet. So if you want to do flux weakening in PMSM, you have to make the current that we are exciting in the armature winding to lead the EMF. So how much it has to lead, it depends on where you want to go, which region. This speed you want, here or here, like that. If you want to go for a very high speed operation, the shift that you will be introducing for the current waveform from that of the back EMF, that will also be more. So up to base speed operation, it is going to be in phase, because you don't want flux weakening here, right? Up to base speed, the current is going to be in phase with the back EMF. So you have the back EMF, current is also in phase. After that, the current waveform is going to be shifted. I'm keeping this as the reference. Current waveform is going to be shifted. Current is going to lead. So if you want higher and higher speed, this current waveform is to be shifted like this. All right. So this one we are not going to show. We are going to explain quasi-square current starting from battery, starting from a DC supply, then sinusoidal current starting from a DC supply. All right. Okay. Thank you.
No, just
camera, you have to shift and you see the line.
आ गया. Hello. Right.
This one is not coming. No, it's coming.
Delay होगा. Okay, so concept wise it is clear that how hysteresis control is done, right? We are going to show all these things experimentally, right? So what we are doing experimentally, I want to explore the system, I will tell you, and the same system is being implemented over here. So what we want, we single we want to connect a circuit, right? Here we want current sensors, right, to sense the actual current, and it will come STM 32F407 VG, which we are going to use, right? It's 32-bit microcontroller. We are getting this current into microcontroller through ADC port, right? And we are writing that code, hysteresis code, inside the microcontroller, and according to that we are getting 4 upper switch, lower switch for single leg and then second leg, right? So if you see the block diagram there, then this is simply I reference and this is I actual, and for single phase inverter, I'm not IGBT based, but switch 1, switch 2. Here DC supply. So switch 1 and switch 2 will be turned on simultaneously, and then S3 and S2 will be turned on simultaneously. So this S1 and S4, then S2 and S3, right? Now, microcontroller does not accept bipolar signal, right? It accepts only unipolar and positive, right? So for this microcontroller, it accepts 3.3 volt, right? Here my current is going to be AC, right? So we need to shift the sensed current, right? So that this come under this range, because microcontroller cannot accept this beyond this. So we can have the signal from current sensor between 0 to 3.3 volt. For that we need sensor first of all, and then what signal conditioning also, right? So if you, I will show you this current sensor, the sensor, and then signal conditioning. For providing offset to the signal, there is port, you can no, there is no that option there, but what for controlling the gain, for how much current you want, how much voltage, it is there. And for offset we have made it fixed 1.71 volt. So whatever provided at the time of sensing in the code, track that, right? So it is shown in the for code. The ideal way, you go assembly language and C language. Most of us are not good in coding. I am also not good in coding. So there is option for you, right? Best option for you, auto code generation, right? It is there with PCM. It is available with MATLAB also, right? So for MATLAB, there is Weijing blocks. It is perfectly compatible be installed as a block set in this MATLAB simulation directory, and you can have each and every function of microcontroller in the form of blocks. Like if you want to use ADC, you can pick ADC and you can it. In the same way it is coded here, right? For that, what I want one ADC, right? Do you plot? Getting one target block is there, right? And for this particular microcontroller, what sampling I need to specify in this target block, right? So, sir, can so this, yes. So if you see, then this is target block, this is ADC, and this is digital output, right? Before, after that, this is ADC. Since ADC is converting analog signal into digital count, so we need to retrieve it via reverse multiplication. So I am multiplying with 3.3 by 406, because 3.3 volt will be converted into 4096 12-bit ADC. So it put into 4096 count. So I need to retrieve that voltage, and then after that I need to subtract the offset provided 1.71, right? And then I need to multiply with sensor gain also. Then we get actual signal, and then it is compared. This is subtracted from the reference, and then it goes to hysteresis block, and we are generating gate pulses, and then gate pulses will be given to digital output block, and it will be given to IGBT card, right? So we have used two signals. See, we are not having actual machine, right? So we have generated the signals inside the code itself. So this is for sine, and this is for quasi square wave, right? So first we will run with sine, we will see how it is working, and then we will see with that. Performance cannot be I mean up to the expectations like simulation. You can have wonderful waveform, but here we are having limitation with inductor, because inductor is iron core. Ideally we need a ferrite core which can sustain the frequency switchings, right? So हम लोग so this is STM32 microcontroller we have seen yesterday, right? This is sensor card. This is sensor card, and I have used the first one, right? Red one sensor, and this is digital output port of this microcontroller board, and I'm getting 4 pulses. Inverter block. Sir, we need some. I'm getting from this DC input to VSC inverter card, converter card. I am applying 60 volt. Okay, so we are ready to run it. So I have given sinusoidal as a reference, and you can, if you want to see stresses, you can see that it is chopping, but not in that fine way of the limitation from inductor side. Have ferrite core, you can get handsome waveform. So is there doubt? Any doubt? Difference to passive square wave, and then we will. अगर आप उस पे जा रहे हो ना बिल्ड उस पे आई मीन you want to shift your code to dump to code, then it will automatically build and it will convert into the code. तो ऐसा नहीं पहले उसको रन करो फिर उसके बाद उसको करो, नहीं वो सही हो जाएगा.
So there are some people who may not know Hindi. I think so.
Okay.
Correct?
He was asking actually, first we need to run the simulation, then we can convert in the code. Right? There is option to dump your program, your code into microcontroller. So I told him there is no need to run this program. You just click on that dump button, it will automatically run and it will convert into the requested code, right?
Yes.
Right? No, it is taking time.
Everybody has to build.
No. तुमने जो पूछा था मैंने वही जवाब दिया.
English.
Yeah, he was asking the same. ST link is not detected. No, I just need to. That port was, I think, not working. That's why it shows that ST link is not detected. So if you are very good in simulation, you want to turn your simulation system into reality, and you are afraid of coding, then this is the best way, right? And one thing I want to tell you, yesterday I was checking this system. This is simple system, and I spent my whole day in that, right? The main difference is when you do this whole system, I mean, copy and paste, you say that gate pulses is connected to this, then it is connected, right? क्योंकि पेन से ही connect करना है. But in reality, there are many issues. हो सकता है जंपर ही काम ना कर रहा हो, right? हो सकता है कुछ और कमी हो. तो जब आप हार्डवेयर पे, when you do on hardware, it is next experience. Yeah. I mean, the sir told that here we will turn off all 4 switches. So I have not kept it that in that way. So I have just simply applied the stresses controller, and then we are getting that. So any question? Huh? I kept, if 1 ampere is reference, then 0.1 and plus 0.1 and minus 0.1. Right. So it became 20 stresses band. Right. So okay. Thank you very much.
Do they need to take a break? No. Continue. It should be fun. Questions ranged everything from we were short of solving global hunger. Other than that, everything else was in the list. No, I'm good. Thank you. All right. So questions you're gonna put up here, right? Okay. You good? Okay, so it is on. Yeah. So, all right. Good afternoon, everybody. Welcome to the last session of this GIAN short course. It's been a lot of fun. This is the last piece that we actually wanted to kind of have a little bit of a discussion, talk a little bit about what you've been doing, the questions you might have. One thing that would be really nice is if this was actually a little interactive. The fact of matter is that I know what I know, but there's definitely things I don't know. So, and there's plenty of that. The point being, I would love to answer the questions as much as I can. But if anybody has a different thought or a different perspective that you might be able to share, please feel free to jump in. The whole idea is not for me to tell you what to do, but it's more to have an interaction at the end. So let's do this. Let's have, we can go in, start with a single question that we have for one person, and then we'll go to the one that has 8 or 9 questions. So let's start with Pradeep Sonkar. Pradeep is Apo. Okay. So Pradeep, your question was, what is better for EVs, long axial length with small diameter or large diameter with small axial length? So in most cases, depends on the application you're going for. So EV, if you talk about traction, when you the general rule of thumb is if you want more torque, you increase the stack length. If you want more speed, you go larger in the diameter. So that's a very general rule of thumb that we normally follow. Axial machine is the opposite. When you want more torque, OD goes up. So in general, if you're talking about a machine in which you want to have a very high starting torque, in that case, the most you want to get as much of the diameter as you can. But there are very hard constraints. The thing about EVs is that oftentimes you're limited more on the diameter than you're on the stack length, because depending on whether you have a differential or not. So if you don't have a differential, then it's a hub motor. But if you have a differential, or not just hub, you can connect it to wheel, or it's sitting inside the wheel. Inside the wheel, the radius is very limited. But so there's no one single answer for this, but generally speaking, if you can, we're always trying to go for a larger stack length. First I said larger stack length, but yeah, more torque is more stack length. So if you get more stack length, that's good. But because if you notice, the speeds of the machines go from about 12,000 to 90,000 RPM. The more diameter we get, the better it can be for us. But your wheel motors are not high speed. They're usually going to be lower speed if they're not geared. which is another whole other caveat, is that you might actually consider looking at something that has the integrated drive with a gear setup built into it. So that's a whole nother conversation. Feel free if you feel like I didn't answer your question, anybody for that matter, feel I didn't answer the question, or you have a different answer that you might have from your experience, please feel free to jump in at any point. And I mean, I won't necessarily ask if anybody has a thought, but just say like, hey, I have something to add. Okay, so let's go with to the next one, which has 4 questions. This is from Sai Ganesh. Okay, what types of electric machines are preferable for all-terrain vehicle applications? That's a very broad and open-ended question. Generally speaking, if you see ATVs, I believe John Deere actually did some work with special transmissions as well. Generally speaking, because you're going for high torque motors, ATVs are, once again, are not very high speeds. So they're all typically going to be high torque. If you have a differential that goes with it, and if you actually have a gear set that goes with it, which in most cases you probably will have some sort of a gearing assembly, it's not going to be direct drive. In a case like that, you would typically go for the cheapest motor. So for ATV, just because you're talking about ATV where the profit margins could be lower. Now, if you talk about off-roading and you're talking about an ATV, I'm assuming we are looking at something more along the lines of a small 4-wheeler, the golf carts, or are you talking about an ATV that is like a Hummer, it's buggy kind, right? Not something like a Hummer, because Hummer arguably is an ATV, but no. So if you're talking about a buggy kind, in that case, you would typically be going for a permanent magnet because space is at a premium. But oftentimes you will end up with a gearbox. Without a gearbox, it will be difficult for you to look for that torque that you need at the very beginning. And the cheapest, sorry, I said permanent inductions. Induction will be your most likely bet, because induction is going to be the cheapest of the motors currently in the market. You might even go one step further and look at something like a brushed DC motors. Brush DC motors will be cheaper. They are more flexible. Permanent magnet brush DC, to be more specific, can actually have a value there, because your profit margins for ATVs all depends on that. If you're buying top of the line, you have some profit margins, but if you're buying something in the mid range, they will go for the cheapest option possible. So induction PM is a toss up there. Then what are the requirements of high tractive efforts, compact IP68 compatible water protection, and reliable under heavy or on-road vibrations? Okay. Got it. Okay, so the question was, what are preferable where requirements are high tractive water protection? So water protection, so if you're talking about water protection versus the motor itself, there are 2 different things you're dealing with. One is the question about the second part is the question about the enclosure. The first part is the question about the motor. So there's nothing called I don't know if I can actually call anything waterproof motor. I mean, like if stuff gets in, things are going to happen, right? So your typical question would be, what kind of housing are you going to need? And you already have the IP code there. So you will have a specific IP protection. The housing will be what you're going to spend some time and money on. But the motor itself, like I said, you would go for the cheapest motor. Normally, I don't think I've seen too many ATVs that boast of a very high efficiency, because very high efficiency usually means you have a slightly larger space and cost. Without that, is kind of tricky otherwise. All right. How hill hold assist, feature available with premium cars, which doesn't allow the vehicle to slip during hill driving. How can hill hold assist be achieved in electric auto transmission vehicles? That is a very specific question about how you would actually be able to implement this. I'm not entirely certain I am qualified to answer a question on the transmission itself. If you're talking about the EV, because keep in mind, a direct drive is one thing, but a lot of times you will have either a motor coupled to the wheel, in which case you would have to apply some amount of power. But in terms of what kind of mechanical setup they would have to hold the vehicle in place so that it doesn't slip back, I do not have an answer to that question. I would have to read through that myself as well, because that's a question of the transmission. And the transmission, I don't have as much experience as I would like to. Yeah, sure.
Is it like brakes will be applied?
Yeah.
So until the wheel movement is detected, so only the forward motion is required, the motor has to come into play.
Yes. So oftentimes you actually end up, I mean, you have in most cases, you'll have a friction brake. So you cannot just have regen braking, right? So you will have a friction brake. So in terms of, so there's a braking, But he's asking about the transmission as well, right? Like he's talking about how the motor will be controlled, because friction brake will get the job done. Somebody says something?
Yeah, normally there will be like a fluid coupling clutch.
Yeah.
That's torque converter.
Mhm.
And then an internal combustion automatic transmission.
Okay.
So what happens? There is a part called as a stator, is like the pump, fluid coupling pump, which maintains the engine RPM, and there will be an RPM maintained in the transmission as well. So what happens when the hill is at when the vehicle is at a gradient? So it doesn't. It maintains an torque, and it doesn't allow the vehicle to come.
Well, for a vehicle with an engine on it, if you are, I mean, yes, if you put it in neutral, because you have a clutch, they are correct. So if you put it in neutral, in that case, it rolls backwards. But if you put it in gear, in that case, it is going to try to move forward. So in terms of, so that would be a question I really would have to figure out. Each vehicle will be different in terms of the transmission of how they do it. I really don't have a good answer for that, unfortunately. So I don't know if on the mechanical, so that's going a little too far mechanical for my expertise. So all right, so let's do this. I'll take like 2 or 3 questions, and then we'll go through the rest. Any other questions we have, that way I'm covering everything. So, and then the last one here is there a possibility to perform a coupled field FE analysis, electromagnetic and structural? What will be the challenges? This is a good question. To my knowledge, I don't think electromagnetic and structural currently has the potential. There is one software called COMSOL. COMSOL is the only one that actually has a coupled model where you can do multiple simulations simultaneously. But normally, if you look at most FEA software, it's sequential. It does one ANSYS, for example, it does one, then the next. There's coupled directly. COMSOL is the only one where you might be able to couple. But the biggest challenge here is that you have to have a very specific information about the housing. So the challenge that comes in is that if you bought the housing, or if you got the housing, can be challenging. So no matter how you do it, you will see some variation. You won't find the modes as accurately as you would want. In doing something like an impulse hammer test and characterizing it, that might be a better way of looking at the structural design and possibly creating a behavioral model from the housing. But by itself, doing an FEA that couples both, I don't think, other than COMSOL, any other software, to my knowledge, has an option. Yeah, they are two different though, right? I mean, the electromagnetics comes from Maxwell, and then the structural comes from ANSYS, Workbench, the original ANSYS, right? So they don't do it together. They will solve one after the other. So I think here he's talking about if you're properly coupling it, where they're actually working together, they will solve one after the other. COMSOL is the one where they actually, as I understand, the equations are actually coupled internally. So they're connected internally because they were designed to be part of the same system, as opposed to ANSYS, where they acquired different software and stitched them together. So yes, you are correct. So ANSYS can do all the simulations, but whether they're truly going to be coupled, we've actually even had some challenges where when we went above a certain frequency, the numbers above 5,000 hertz, ANSYS was not putting out the right magnitude. Our decibel levels and our vibration frequencies were not reading properly. So we had some challenges there that we found out several years back. It's a good option definitely. You can look at it, but you have to be careful about, you have to have the exact dimensions of your structure. That's a whole nother thing, which is possible, but a manufacturer has to provide to you.
We have projects with coupled field analysis. We used to work with structural as well as thermal parameters, but not with electromagnetics. I don't see people.
So what did you use for coupled thermal and structural?
Like internal combustion engine.
No. What software?
ANSYS, Workbench.
So everything was, so what was part of the original model. That's the only reason I don't. So to your point, I'm not, I guess, in my experience, I don't know that they actually work together quite as cleanly. But I would not go as far as saying it's impossible. They might have done a lot more since we tried it. Okay, so going up to the top, okay, out of FOC and director control, which control method is widely used in existing EVs and why? Normally, you're using a field-oriented control for a faster response, right? You want a faster time transient response. So oftentimes, you will see field-oriented control as a good option. But if you're trying to do a traction motor control, DTC control is somewhat simpler in its implementation. So depending on, once again, which kind of motor you're picking. If you're doing EV, FOC kind of beats everything, but direct torque control can be a very viable option for permanent magnet motors. So even for low speed drives. Okay. Okay. No, better, once again, better is an unfair word to use there. FOC is more effective for a very specific purpose. So it really depends on how quick, how much, because your transient response is going to be much better for FOC, right? So in terms of DTC, it can go to high torque capability, it can run it like that. But typically, if you're going to higher torque regions and you're going to very high torque regions, you would end up usually going to direct torque control. But that is not to say that people have not tried FOC. In electric vehicles, like I said, if you look at induction motors, oftentimes you will see FOC still be talked about. So that's once again my experience. And then which battery technology is most suitable for BEVs and marine vessels? That's a, once again, very specific question. There is not a good answer specifically, because that couples to the next one, the batteries and fuel cells, which is safer to adopt in EVs. In my experience, lithium ions still rule the roost. I mean, there is no good contender that can replace lithium ions quite yet. We are getting there. There are people like even solid state batteries have a very strong potential. What could change the game is if we find something like sodium air battery or something that actually gives you the required power density. People have been trying to get rid of lithium, or have been trying to not use lithium if possible, and use something that's not going to be a challenge in the environmental sense. So people are trying lots of topologies, lithium air, sodium air, and then you have even solid state cells and everything. So there are people who are trying it. In marine applications, once again, the question would be, what are the parameters of your application? If you're looking at high power density, in that case, looking at a combination of batteries plus ultra caps might be an option. The hybrid energy storage system rather than just one. But if you're talking about using something where safety is a big concern, then in that case, perhaps staying with something a little safer, lithium ion would probably not be the top. I mean, lithium polymer phosphate had some potential, but now it's been largely replaced by lithium ion batteries. So LTO is expensive. So marine you can do, but LTO is it's by definition is titanium. So if you can manage the money, which in marine application they might have the money for that. Lithium titanate normally you're going for a lot of times because it is extreme fast charge capable. So you're looking for very specific reasons. So if LTO, can it be used? Yes, but you have to have a good reason. Just because you can, I don't know if you should. Once again, I'm not arguing that you shouldn't. I'm just saying I don't know. I haven't looked into LTO for marine very specifically speaking. That. Mm-hmm. Okay. Okay. Wow, we are getting very personal. I don't know. I mean, I can only assume if it's technical data. So I would. So normally I like benchmarking reports done by any labs that you see that are not from that specific country, ideally, or if there are manufacturers, or there are not manufacturers, researchers who've done that. But is it reliable information? I mean, if it's been patented and if it's been followed through, there's a good chance what they're doing is right. But there is never a guarantee, right? Volkswagen said that they did not have the emissions they had, and then we found out their emissions were way, way worse. So whether the information is reliable, I mean, if a German manufacturer can do that, why cannot Japanese or American manufacturers not do the same thing? They could do the same exact problem. So yeah. Right. Right. So sodium is right now is very popular. You also have things like silicon anode. So where you can actually, there are topologies where you have silicon anode that are used for batteries to increase the power density and such. So there are lots of advancements happening. Our bottleneck right now, as I see it, is lithium and the supply chain volatility. So sodium by nature is going to be easier or cheaper if we can get to cost parity. That's always the question. Can we get to cost parity? Right. Ooh. Fuel cell is expensive because your electrodes and everything that you're using are expensive. So in terms of safer to adopt, fuel cell tends to be a little bulky because you have to have a reformer. Let's say you even take the reformer off board and you're only putting in hydrogen directly, not even ethanol or water or anything. Now infrastructure gets expensive. So in terms of safety, the hydrogen tank is heavier because you normally put it with manganese pellets or something. So fuel cells, the entire system tends to be heavier in my experience. So we have cars like the Mirai. The Toyota Mirai is an FCV. Honda Clarity, yes, Honda Clarity was an FCV as well. So there's another one, FCX, which is also, I think Honda FCX, I think it's also called. So there's a few vehicles that are fuel cell based vehicles, but normally it's not so much a question of safety. It becomes more a question of hydrogen economy. The amount of money you spend on converting ethanol or water into hydrogen and then converting that hydrogen into usable fuel, it really comes down to how much do you spend at the front end and the delta H, and how much did you get at the other end. If the delta H is not enough, then you have a problem. So now we can offset when you generated and when you used it, but other than that, you might not gain enough energy. There's also another battery called a zinc air battery that was tried for quite some time, has very high energy density, but then it also converts all the power or the zinc into zinc hydroxide, sludge. So it's difficult to move solids. So there are different battery types that are available. In some safety, zinc hydroxide, zinc air battery is very safe, but it's very difficult. So once again, I have to unfortunately say too many answers. Okay, so which motor might be, okay, which one? That's okay. So let's see. Let's go to the next page so we can come back to this. 8 questions here. We'll do 3 questions and then come back to the next one. Okay. Praveen Kumar has a question. Praveen is, yes. Okay. ID can't correct. Which motor can be a good choice for region braking for the EVs? In most cases, motors currently in the market for EVs are still permanent magnet, mainly because you're able to control them. Induction is a little more complicated in the control. You need something like you have to go super synchronous. You have to be running with FOC to kind of get the power out. For if you want to get region braking, in most cases, you are still looking at, you might have a PM assist or variable reluctance. So there are topologies that are currently have been very popular, which have a PM assist to reduce the amount of permanent magnet. I have so far not seen anybody who says that eliminating PM altogether, especially for region, would be the best, because it's fine for traction application, but the moment you start generating from it, your efficiency is like a switch reluctance machines for a generator is fine, but I would not put it in the top 5 or top 2. So PM machine, some version of PM assist motor, there are several topologies. PM assist alone, there's a slew. You have ferrite core, ferrite assist, you have neodymium assist. So one of them would be better suited, even if it's not a conventional IPM. So Swati's question is, sorry, Swasti. Swasti is, right? Yeah. So Swasti's question is, in high-speed operation of switch motors, when we advance turn-on angle during the flat inductance profile, that current will contribute to copper loss only. How to, I guess you're asking how to handle that. During the flat inductance profile, you're talking the bottom or the top? The unaligned? So yes, so at high-speed operation, when you do phase advancing, you will end up with current that contributes to copper loss. You have to extract it. I mean, if you're doing phase advancing, you're basically moving your current profile to kind of overlap with the next phase, right? So you're giving it a little longer. But once again, there is an element. If you go too far into it, you will generate a lot of heat. So that is a variable. So you have to have a secondary. So first function is torque ripple, but the second one is heat. Heat can be a bigger killer than ripple. So acoustic noise you might be able to handle, but extracting heat can lead to a subsystem that has to be over-designed. So I would almost say is that something that you actually are facing in terms of heat?
Yes, sir. Whenever we go in hardware implementation, then it will create a lot of issues. Because during that period, as inductance slope is 0, so obviously no power will be
Right.
So it will also contribute to losses.
Like I said, when it comes to heat and losses, the only way you can do it is you have to extract that loss. You have to extract that heat. So you can look at options like passive cooling. You can pot it and you can kind of send the heat out to the stator backyard and extract it. But in terms of, if you're talking about a peak power, you could look at something like current shaping. One option could be possibly that don't apply full current. So when you're doing when you're doing the phase advancing, possibly see if you have the option of controlling the current at a different magnitude. So you're still getting some overlap, but you're minimizing or you're reducing the not just negative torque, because keep in mind, if you go too far, you're going to get negative torque. So hopefully you get to a place where you're able to get the heat out. Basically a step function that allows you to change the current could be one option. But in terms of if the heat is already there, copper loss equals heat. If the heat is already there, other than extracting it, there's not much you can do. When you have to find a good thermal management system, you might even have to over design a thermal management, which now becomes expensive. So I'm giving you guys a lot of answers that says that unfortunately there's nothing you can do about it. That's not quite what I mean to say, but research by definition does that. Right. Well, yes, but what she's saying is she's using phase advancing, so she's overlapping on purpose. So she's allowing the current to go further from the tail of the current. She's extending it a little further and allowing them to have two phases that conduct at the same time. So she's saying at that time, because she's applying current to the flat top, she's getting a current. So it won't necessarily, actually at the same time, your copper losses won't be that any more than it was otherwise, right? I mean, you're applying the same amount of current, your copper losses would still be the same. I square R stays the same, aligned or not aligned. The only thing that would change is you're going to send that energy into the core. So that's where I think that's where you're going to have more of an issue, not the copper. Copper, whatever you had before is still going to happen. So I square R stays, the R stays the same. So I square R should not change. But your core loss, hysteresis losses, that might go up. Which means, oh yeah, definitely. Yes, that's what it will be. All right, so how to start the SRM initial position during starting? So there's two ways of doing it. One is basically hard start, which essentially you apply current to one phase, put enough current to where the closest rotor pull aligns itself. Either set it up to where you have an optical encoder or you have a Hall sensor or something that allows an optical encoder or sensorless method to initialize it. So basically you set 0 and then you initialize with an incremental encoder. Alternately, of course, you can go completely sensorless, in which you start the mechanism, because the rotor, if it maintains this position, then you have no problem. So we actually have a few patents that we have filed and we've been issued where we had quasi methods that allowed us to basically quasi sensorless methods that allowed us to use a notch on the shaft that combines with the current profile that we are getting. So there are ways to do that, but if it's just talking about initialization, a lot of times people in the lab setup, you would do a hard alignment. So apply current, it aligns itself. But in a real setup, you would either have a position encoder that gives you the feedback and maintains it using an absolute encoder, or you would end up creating an offline observer that maintains the position. You don't have a way, like you saw what I had done for one of the methods I showed you, that actually was for standstill. Yeah, if you have a specific inductance profile, you can use inductance directly to calculate the initial position. So initial position sensorless, there are several methods, but if you want to do it in a way that is very reliable, oftentimes people just toss in hard alignment. But that's not very practical for hardware setup, because you don't want to start a car and apply current and the wheel spins one direction. You just don't know which direction. That'd be terrible. So, all right, so let me go to this one first. I'm working on thermal management system, lithium-ion batteries. Can the phase change material together with mini channel cooled liquid cooling system be used for better cooling? Can we use similar technology? Used in EVs if they need to be operated for a longer duration in high ambient temperature? What improvements can be done? That's a lot. Okay, what improvements can be done in winding materials and winding arrangements used in motors of EVs for improving efficiency? Wow. Okay, that's a lot. So let me ask the first one. Is it? I know, it's like the whole thing is one single question. So, is it possible? Yes. Modithya. So yes, is it possible? Yes. Combination of phase change with liquid is actually possible, and it has been done as a matter of fact. In terms of liquid, talking about micro channel, mini channel or something, if you're talking about using something like a what's the fact? what do you call it? The one in which we absorb it from, if there's this with a small pipe, it basically absorbs. What's that phenomenon called? Capillary action. Thank you. If you're doing capillary action in which you have a very thin tube and you're trying to use capillary action to pull out the liquid coolant through it, that's different. That's I don't know much about. But if you're talking about mini channel, meaning you're using a pump to run it through, yes, with the cooling channel, it's been done. There actually are some works. I don't know for motors or not, but they have definitely tried. In fact, even for PCC, you can use different shapes. It doesn't have to be just a potting. You can even have different shapes that are placed inside the slot itself. Can we do this for motors? Yes, in theory you can. I haven't seen very many people who've done this effectively. They use potting material with epoxy and such, because PCC sometimes can be conducting. In particular, if you're using something like graphite, it can be conducting. That can be a challenge. What improvements can be done in the winding and materials? Arrangements used for improving efficiency usually is going to be slot fill factor. Put more current through it, put better material for laminations, and pump as much current as you can, extract the heat. So combination of high slot fill factor, good cooling system, and good material. That basically means design a really nice motor and you'll get good performance. Otherwise you won't. So there's no good way of saying that. What's the scope of axial flux SRM? That's actually a slightly challenging question to answer. There is a paper, in fact, on the Google Drive. I actually put a link specifically, which I can share with you. There is actually a paper that's looked specifically at the scope of axial flux switch machines. I put that link on the Google Drive, which Ankur hopefully can share later on with you as well. But there are options for axial flux machines. There's nothing that stops you from doing that. We, in fact, built an axial machine. We were doing that. No, it was a radial machine, but it was a lateral movement. Axial machine is very possible. In terms of application, you would be limited by what radius, what diameter, and what length you're able to handle. Oftentimes, your winding space might be a challenge for axial machines, since you don't have a second source of energy. You don't have a permanent magnet. That means if all the current is coming through this to the winding. Maintaining that 0.1 to 0.2 millimeter air gap is also challenging, because here you don't have a bearing holding it in place. You have a linear bearing that's holding it in place. So that it's a little bit of a challenge. It's manageable, I would imagine. People have done that, but I haven't seen any application. Even appliances, I haven't seen that being done. Axial machines. PM axial, I have seen, obviously YASA and such is axial. Okay, industrial challenges and future model of the EVs. That's a very, I'm not sure. Industrial challenges and future model. We talked about a few of them today. So in terms of what challenges exist in EVs, there are several. The first one I would imagine is customer hesitation. Is people are afraid, and upfront cost. So upfront cost is a very important factor. We also, the back end problems basically would be grid integration is the big thing. And in my mind, chemical waste. So electrochemical waste is a huge issue that we are not quite planning for. Grid integration, we recognize it's going to happen. We know it's going to be a problem. So in involving renewable energies, creating a microgrid, I think the idea of a microgrid has tremendous potential, and doing localized distributed DG concept, I think has tremendous potential to solve a lot of the problems that we might end up seeing. But the idea of battery and creating chemical waste remains an issue. Design algorithm for PSM. That is a very, very open question. There are books written about that. So I can point you to one book. So this was Shubham, right? I said Shubham. So there is a proper book for PMSM machine. There's actually one by Jim Hendershot, which is actually a very good book. He's PMSM book. There's another one by Dwayne Hanselman. His book also on PMSM machines specific. So he talks specifically about machines. It's not super advanced, but it goes into the details. The entire book is PMSM. You want to go analytical? There are a couple of books by Professor Tom Lippo, who's done a lot of work, and he has a couple of books that are analytically, I mean, they're phenomenal. So that's like 3 or 4 books worth of content that I can share with you, literally share with you, not necessarily say it out, because I don't even know if I know everything about them. Okay, so all right, so got that. All right, I'm going to this really quickly as if I'm on a mission here, but bear with me. Is there another page, as I said? Okay, that's the one. Okay, so what voltage level is used in electrical system architecture of an EV for four-wheeler? Typically, if you're talking about the low voltage system, you're still in the 14 volt or 12 volt DC bus. For a high voltage system, depending on the motor or depending on the vehicle, Prius has the 650 volts right now that they're using. They are looking to go to the 800 volts DC bus as well. But the limiting factor here tends to be whether or not you want to have a DC-DC converter and how many cells in series. So that's always the trade-off. Either you could have fewer cells in series and then a DC-DC converter, or you can have more cells in series with a more sophisticated BMS system and then skip the DC-DC converter. But that means now high voltage, high current. So now your pack can be a little more cumbersome in that regard. But 48 volt system definitely is making its way in at this point. That's been around for some time now. It's not like the 42 volts, it hasn't gone anywhere. But there are some people who are trying for medium voltage DC transmission. So medium voltage DC at 1.2 kilovolts with GANs devices. There is some work going on. I haven't seen anything commercial yet. I think 800 right now is the upper limit of where the DC link has kind of landed. And that's what we're talking about today. Yeah, correct, exactly. So that was correct. So I see, in fact, yesterday's questions, I'm glad that I actually touched on some of these questions this morning because yeah, it was helpful. I'm glad that people are thinking about that. Does the area of electric vehicles have scope for electric motor design? That's a very existential question, all right? Or has the technology matured? There is a shift in focus towards subsystem like power management, battery assessment, and so on. I would say yes and no, in the sense that the space definitely is matured to the extent that a lot of the low-hanging fruit has already been taken. So what we are doing right now is all oftentimes tends to be around supply chain and manufacturing issues. So there are lots of issues that we have not handled or solved yet, like for example, manufacturing, materials. So motors has a lot of potential, but not in my mind. I don't think it's classic control strategies. Control strategies by themselves, I don't think they have whole. It's a fruit that's been squeezed out of all its juice. So that's my thought. But I would say at this point, if you combine things like thermal management, cooling methods, materials for the laminations, the winding methods, motors definitely has, in particular manufacturing, has tremendous potential because we still don't do it well. Most of our motors are still coming as the Frankenstein system. We get pieces from elsewhere. So if you can create a localized opportunity for building your motor and also for your supply chain disruption to be minimal, you might have a very strong case. Switch reluctance machine, that was one of the selling points. It's only copper and steel, so it works. But if you go further and you start talking about Hyperco 50 and all of a sudden your alloys change, it gets a little more complicated there. So, all right, so please, at the same time, the battery one, the BMS and everything, yes, that's hot right now. That is definitely hot. I mean, right now there aren't enough people. But the thing is, companies are still hiring. So as far as I can tell, motors, people are still getting hired left and right. I have more application requests than I have people for both topics. Rishabh, okay. But no, we got that, right? Axial flux. We got the axial flux. So this one is, yeah, so we can go. Yeah, the first one. In field reconstruction, okay, which tools are recommended for parametric study of motor design? ANSYS has a very nice parametric models for designing a model. They actually allow you to change the variables in the system. So off the bunch that I've seen, I found ANSYS to be the most practical. My students use that as well. So you can actually create a range of values to do all the simulations. It's still setting up the model. It just automates the modeling process and runs all the simulations for you. And then you can also create a plot from it. So that's what I found to be the most effective. Oh, yeah, she said one before. In view of fire accidents in EVs, what are the lapses in existing BMS? So there's a lot going on right now. So in fact, they're even trying to figure out which one culprit they should be going after. In some cases, for example, there's gasification that can happen, which means you have to design your battery, the cell itself properly. Right now, one of the things that you do need to be looking at is, in my mind, you have to have prognostics. You have to start looking at state of health very carefully. You cannot only look at markers that tell you when the cell has gone bad. So SOH is a very important factor. SOH connects very nicely to state of charge, but including terminal measurements, you need to find a good way to identify what the BMS is going to do. Oftentimes, BMS tends to be an on-off system, meaning something goes wrong, you turn it off. Now the BMS, the way we are designing it right now, in fact, what we did I have an existing patent on that, was estimating the thermal state of charge for a lithium-ion pack, and specifically using that to create a framework that allows you to monitor temperature at the same time as you monitor state of charge. So it has to be a combination of electrical plus thermal. If you don't do that, I think you are always going to be missing something. But we don't care. I mean, the way we are doing it, we don't care. We are looking at the pack. So we are still using terminal measurements. So we don't care how it's being charged. We're just using terminal measurements of voltage and current to identify what the state of health for the pack is going to be. So the BTMS, or the battery thermal management system, is something that definitely. So we have a few papers you can take a look as well. We've submitted a paper on current dumping, where it's talks specifically about a cell going bad and how the neighboring cells react. It's published, I think, in IEEE transactions, one of the transactions. So we published, oh no, it's in applied energies. It's in applied energies. So we published that some time back. So you can take a look at that. It will give you some ideas on that. Field reconstruction basic functions, that actually is a field distribution. So you define for the unitary current, you apply a magnetic field, you create a basis function. It's basically is a sinusoid, is a sum of sines. It's like a unitary method. So it's like a unitary method, 1 amp current, field distribution, permanent magnet, field distribution. So both of them, you're basically decomposing a field into a bunch of mathematical terms, just like Fourier series. So that whenever you want to change the current, you just change the current, multiply the basis functions by the magnitude, you now have whatever current equivalent you want. Let's say you did it for 1 amp, you want 5 amps, multiply the whole thing by 5, add permanent magnets. Because PM doesn't change, all that changes is the winding current. So how to achieve traction motor design constraints. This one I could not, actually I read through this, I could not figure out what this question meant. But let me go to the last one first. Is it possible to have a 4,000 RPM traction motor? That's challenging. That's challenging for any motor. I mean, 4,000 RPM, 500 Newton meters. I would almost think that adding a gearbox in there, an integrated gearbox, makes sense. That would be the most practical way of going about it. I cannot imagine a scenario in which 4,000 RPM, 500 meters, sorry, 4,000 Newton meters, 500 RPM. Your control will be fine. Either you'll end up with a ton of ripple, because your motor, when it runs at that low of a torque, your losses are going to be massive. Your I is so high, your losses are going to be massive. And on top of that, you will end up with ripple as well. So the way I see it, I think for something like that, typically you would have a geared motor, and an integrated geared motor would be ideal. You would have a planetary. So if you look at, for example, bicycles, they have a built-in planetary gear. So if you buy any of the e-bikes and you crack it open, you will see the magnets are placed on it, and then on the housing, and then you have a planetary gear that is connected right next to it, which basically gives you that high torque, because the motor needs to run at higher speeds. So by putting that planetary gear in there, it gives you a higher torque capacity. So this one, to me, it almost screams a planetary gear system, or you might even need more than just the one, but you would need a fairly sophisticated planetary gear system, because the step-up ratio, if you want to maintain the losses, would be quite substantial. The last question, this one I did not understand, Vidyasagar, is short circuit current equals peak load current. In what way? What does that mean? Mm-hmm.
The short circuit current, then even if short circuit happens, that will not damage the winding. This is the constraint how to follow to design traction mode. That's what enhances related papers. So I try to achieve this constraint with different combinations.
But I mean, I'm not sure if we're actually missing two or combining two different things here, because when you go to a peak current, you're also going to cause a lot of heat. So when you go into that scenario, the question is like, what damage is your heat doing, right? I mean, so whether or not your winding is going to carry too much current, I'm assuming what you're saying by peak current is that the thermal system can manage the peak value of current, right? So if you're talking about peak current, to be safe operation during critical faults, I don't think it's an apple to apple comparison. Faults is different from peak power. There is a breakdown torque. So if you go above a certain current, the motor breaks. You can have peak torque, but there is something called breakdown torque as well. I mean, beyond which it will break. So the same way in your winding, I'm hesitant to even to go with that. I would need to check to see exactly what the statement is supposed to mean. But short circuit current and load current being the same could be designed in a way that the current it has its own threshold where you basically saturate or something. So you could create it like that, but I don't think it's a default mechanism in any motor. I don't know if I can think of anything. Is it?
Is this a motor designed for tolerant for short circuit fault?
Yes, sir.
Oh, I
This
see.
is a motor. He is looking for a motor which is to be designed for tolerant.
I see, I see, I see. So you are looking specifically for a motor that you will be able to handle something like this.
But the normal performance will be weak.
Yeah.
Because you are trying to address a fault tolerant motor, but regularly, if you move, it's in normal situation.
Like you even talked about this morning as well, the idea of the inverter. That's what's it called? This not staggered inverter, but a shifted inverter, I think. So that idea basically was you would have less current. So even if one gets damaged, the other one continues to operate. Or if you have a double layer winding, for example. So there are ways in which you can manage, and dual layer winding is something you can take a look at and see if that's potentially an option for you, where even if you have some fault. Short circuit can mean many things, right? Interturn short, you can have a phase to ground short, you can have many kinds of short. So which short we're talking about also plays into this decision. But things like multi-layer winding, dual layer winding and such might have a possibility here. But I would need to look specifically to see how they're doing fault tolerance. Professor Raghavan is right in the sense that to create something that's fault tolerant, usually you're giving up something. If you are trying to make something work to be more fault tolerant by creating a secondary subsystem, you might be lowering the efficiency another subsystem, then the overall system efficiency goes down. Or alternate number two is you have basically changed the system configuration altogether, like change the number of poles or something. So I was too sudden. Swasti, I have no question. Okay. How to deal with stability problems as well as bearing-related issues when we go to high-speed switch reluctance motors, or any motor for that matter. Stability issues and bearing-related issues. So what kind of stability issues are we talking about?
There might be some like from electromagnetic as well as from thermal management point of view.
Mhm.
So just like if the frequency crosses whatever the critical frequency that is being defined when designing the motor, then what will happen?
What will happen? When you go to high-speed switch reluctance motors, typically we select bearings that are high quality. That actually is one of the limiting factors. If you don't select the right bearings, you can actually have vibration. You can actually have the bearings that go out very quickly. So generally speaking, it is a function of cost, about lubricant for the bearings. You cannot buy something that's super cheap. That's the only answer I can think of. Other than that, you can do active compensation. There are some active compensation methods that specifically allow you to lower the vibration you get. But keep in mind, that's not solving. So you can do active torque ripple mitigation or active vibration compensation for systems, just like a Bose does. Basically, you can try to muffle out or clip certain frequencies. But in terms of the design stage, you need to have a bearing that actually is going to have a lubricant that can handle those speeds. Otherwise, the lubricant can harden. It basically get very gummy or hard, and it'll start to then crack and break. Okay, I was like, did I answer the question? Okay, if I did, if you say I didn't answer the question, that's fine too. I believe you. What challenges that what are the challenges that in general faced by electric machine designer while they move from simulation to hardware? That's a great question. Everybody needs to be aware of the fact that there are real problems when you do it. Oftentimes, simulation overestimates. So numbers are almost always not always. Most of the time, the numbers are going to be higher than what you get. It also ignores a lot of times harmonics. It also ignores parasitics. So in terms of simple implementation, like we had the demo today, one of the things is you have to know how to write code. If you write code yourself in C or something, that is always better. I grew up writing in assembly at the beginning and then C. So using Simulink is something my students do, but I'm not fond of that idea because then it doesn't give me the control I want. It's like having an autonomous car. I can only give it so much control before I get a little anxious. So Simulink is great option for people who want to do it. But generally speaking, the simplest or the best way to do something like that for hardware implementation is you have to have full control over your code. So at some point, no matter what you do, you will have to switch back to looking at the code yourself. So you can start with a code that is generated, but eventually you'll have to get your hands dirty. But in terms of implementation details, you definitely will have losses are going to be most cases. They're too ideal. For example, temperature change, a lot of the secondary effects, like you're running the motor and it gets hot and the winding resistance changes, your simulation never sees that. So in reality, your simulation, your hardware will see that, which means there are changes, so your control will not adjust. So you have to start aiming towards robustness as you're operating, no matter which motor you're looking at. But implementation, generally speaking, you want to have more control than the system does. Otherwise, it'll be challenging. But once again, I'm not saying the hardware setup is good. It is useful. It's a very good tool to have. Simulink has done that. PSIM has done that. They've all done that. It's very nice to have that option. Conversion from your model, control model to this, to your system is very nice. My students do that. I don't. So.
By any electrical machine designer.
Yeah.
It is by Swasti.
Oh, I see. Yes, correct. There you go. So, yeah. So this is, so if you are doing this, the best, to be honest, the thing that you're doing, if you're doing an if you are designing an electric machine, the simplest thing to do is double check your work. One thing, like I said before as well, one of the issues we had was we had the transformer backwards. We've had the wheels that pop out of a car. We've had the windings that got completely ripped because somebody saw it or didn't see it and they didn't say anything. So always double check your work. But in terms of implementation, always get a second pair of eyes. Try it a couple of times. You will fail a couple of times. It's okay. If you don't try it, you will never know what's going to come. But when you're implementing this, expect that the numbers will be lower. That's almost always going to happen. And pay a lot of attention to your gate driver. That I would say. So whenever you're designing something, one of the key components you're going to be is a gate driver. Switch selection is important, but the circuit makes or break your circuit in most cases. And noise, cable length along with noise. Now I'm giving you everything. So cable length and noise are connected, but looking at gate driver is important. And the last one, what are the factors that need to be considered while optimizing the electromagnetic design of an SRM? Very SRM's focused questions. Your PhD SRM, right? Okay. So optimizing electromagnetic design, I gave you the full download on the design parameters for the SRM. Your primary objective is going to be looking at your saturation level for your motor and how much heat you're going to generate. Torque, ripple, acoustic noise are big issues that you always have to deal with. If you ask the question, 9 out of 10 times people will say, how noisy is it? If they know SRM, the first question they will ask you is, how noisy is it? So be prepared to answer that question. Be prepared to give them an expectation of how an SRM is going to be better than a PM machine. You will always get that question. So you have to have a good case there. In terms of optimizing electromagnetic design, make sure you are not making your rotor poles too thin. That's one thing. Make sure your shaft design is not too small, because if your shaft design is too small, it can have bow a little bit. And when it bows, basically, it will create more axial vibration. Sorry, more eccentricity. And the eccentricity can create a lot of problems also. So if you have size your shaft design well, there actually are papers written specifically on shaft design. When you're doing that, make sure pay close attention to shafts. They are important. It looks like it's just something to hold a motor. It's not. It's a lot more than the top button of your shirt. It does something very real for you. So shaft design is very important. And in terms of, that will basically be the ID of your rotor and the thickness of your poles, which will dictate how much flux density, what saturation levels you're going to get. Your system tends to get more non-linear as you go forward. So you have to make sure those localized hotspots are either managed or they are designed appropriately. Flux barriers in SRMs are somewhat tricky. They can arguably be done, but I haven't seen anybody who's done it really well. I don't think so. Right? At the same time, ask questions. Once again, for anything you guys are doing, I know I went through these questions like I was on once again like on a mission. But if you have any questions, you're always, more than welcome to talk to us. Like there's a few of us here, faculty, and especially Professor Raghavan's been doing this for quite some time. So feel free to ask us any questions if you have anything you want to discuss with us, whether you want to collaborate or just get some information. We'd be more than happy to talk to you. But otherwise, thank you very much, guys. This last hour, I feel like I kind of went go, go, go. And you guys did an amazing job in bearing with me. I hope what I was saying made sense, because I was speaking fast even by my own standards. So, and that was fast. So if you don't get a chance to understand, if you didn't understand what I said, feel free to go back to the video, slow it down 0.5 times, and it'll be right at just the proper speed. Yeah.
One question from my side, what are the applications of application of motors in more electric aircraft?
Oh, their MEAs are right now motors. If you look at them, actually, depending on which site, if you're looking at a twin jet versus, rather a twin jet size plane versus all the way down to a 787 or something, motors play a very critical role. There is AIAA does a lot of work. This particular year, in fact, there was an ITEC conference that happened in Detroit, in California, and they combined with AIAA. So there were several very good papers on motors that came out from that conference. So in terms of application, high power density is super important. Reliability is one of the most important components for aerospace. So aerospace reliability becomes your top contender. So nothing else beats that. So anything that you can use to convince people that your motor is more reliable is going to get their attention. So, right. Thank you, guys. I really appreciate your time. Thank you so much. And I hope I get to see you guys sometime very soon. Right. Take care. You're chopping DC voltage. So they might you'll be filtering what shows, because if you have very good discipline cap and everything, and it's maintaining your smoothing and everything is being done very well. So sometimes your filtration is not on the number of levels, even it's also on your. So I mean, I have my couple of my students who went test that, maybe try it. So,
Still there, I think. Definitely.
Not working machines.
This is what converters on. I am studying multi-level inverter, like for HVDC application for high and power drives also. So I'm trying to focus on modular.
Ankur.
Yeah, it is there. Very recent. Not that mature. Some issues are. बहुत सारे.
Shall we? Can you make your question?
I told one sentence, na? Made one sentence. Definitely, I'm not going to work in machine, and I am under Dragman sir. So yes.
MVDC or HVDC is a good option. There's nothing wrong with it, but you can also do IMDs, more integrated drives. Yes, it's a very good option. It's not a market.
I mean, there under you, someone functions are working on it.
IMDs right now, no, IMDs, I'm not doing IMDs right now. So I right now, most of my work is motors and a lot of it is batteries. IMDs with the managers will be. So I have some work that we have been doing, but for companies. Nothing.
I'm asking because I will come to know that what is going on, not for seeking opportunity over there. I am here only.
And then I'm more than happy. I mean, again, there's a reason specifically why you feel I can help. You can go to Dr. Raghavan, or and you can through him reach out to me. If I know the answer.
No, we have a provision to send the student for 6 months or 1 year. If you want to go, you can always go. So
If it would be helpful, then,
initially he said he will not, he will be with me. He's not exploring opportunity.
So I think you're right.
No, yesterday we spoke to director and there are provisions. We can transfer the student also permanently.
But when you get to a place where you're looking at topics by biology,
yes.
Yeah, but if you look at MLCs and everything, integrated drives, there is work on Tom Jones, who's going to manage he's Thomas Jones. He's a very senior faculty. He's doing machines for these Charlie South. I think he just retired. So it's very good machines.
Time is up for the feedback form. Right, 2 minutes.
They do some MLC and integrators. MLC may, it's definitely is. I see proposals right now on MLC coming up. People are trying. So they can put an even modularity consists.
Certificate. See, nobody will see from there.
Exactly. So that's precisely what the problem is. Stability ka bahut zyada. Sheldon sir is doing everything. He is doing some work. I think Akshay Rathore does some stuff. Sheldon, but by the way, I know him. He's a good friend. He's a good friend.
Ankur. Yeah, everything is recorded. Okay, thanks a lot. We have almost come to the end of the session. Professor Magesh Krishnamurthy nicely started with different topics, starting from overview of motors used in HEV and EVs, then exploring multi-physics energy conversion, and especially focused on induction motor and how that induction motors are being used in electric vehicles. And then fourth day we had on switch reluctance motor, a very detailed discussion we had. And for almost all the topics, he made use of commercially available EVs for almost all the different topics. Literature review by him is very rich. So generally, whenever I used to take class, I don't bring the literature review to that extent. So that to take that aspect I will have to incorporate, although it may be difficult for me. But literature review by him on different topics is very, very rich. The quantum of work is also very high, and you covered all the topics at a nice pace of instruction. It's very good. The course should have been a little longer. So with 5 days, this is what is possible. So now I thank Professor Mahesh Krishnamurthy for readily agreeing when we made the proposal before 3 years. So it is very nice of him. So let us thank him by. I request him to issue the certificates to all the participants.